Structural Analysis of the Generalized Collatz Tree, K-Tree. February 4th, 2026. Abstract. In earlier work, reference 1, we introduced a refined and more structurally representative Collatz tree within which we identified a singularity. A subsequent preprint, reference 2, established a methodological generalization of the Collatz sequences that preserves this singularity by extending it to a generalized singularity. In the present paper, we investigate the structure of the generalized Collatz tree, referred to as the K-tree, arising from this transformation. Our analysis focuses on the ordering, propagation, and interaction of branch beginnings across ranks, with particular attention to the structural sets B sub k and A sub k. This study aims to elucidate the internal architecture of the generalized tree and to clarify the extent to which the geometric and dynamical features of the classical Collatz tree persist under the generalization. Introduction. The Collatz conjecture is traditionally explored through the inverse Collatz tree, whose root is the integer 1, and whose branches encode all trajectories, eventually reaching this fixed point. Despite its apparent simplicity, the structural organization of this tree has long remained insufficiently understood. In a previous preprint, reference 1, we proposed a new formulation of the Collatz tree that more faithfully reflects the internal dynamics of the Collatz map. This construction revealed a recurring structural phenomenon, referred to as a singularity, that is represented by rank 1 branch beginnings. Building upon this discovery, a second preprint, reference 2, introduced a methodological generalization of the Collatz sequences. The purpose of this generalization was to preserve the intrinsic binary singularity of the classical system while extending it to a parameterized framework governed by a transformation of the form 1 plus 2k times n plus s sub k of n, or n divided by 2k, depending on the congruence class of n modulo 2k. The present work continues this program by examining the structure of the generalized Collatz tree denoted as the K-tree. This tree is generated by parameter-dependent branch generators. Our objective is to analyze the behavior, ordering, and propagation of branch beginnings across the ranks of the K-tree. And we are not aiming to provide any proof of the Collatz conjecture. 2. Generalized Collatz sequences 1 plus 2k times n plus s sub k of n and n divided by 2k. In the previous work, reference 1, we first defined two auxiliary functions, g sub k from e to the natural numbers. G sub k of n is equal to n divided by 2k. Here, E is the set of strictly positive natural numbers that are congruent to 0 modulo 2k. Next, f sub k from L to the natural numbers. F sub k of n is equal to 1 plus 2k times n plus s sub k of n, where s sub k of n is equal to 2k minus n modulo 2k, and L is the set of strictly positive natural numbers that are not congruent to 0 modulo 2k. K is called the exponent parameter. The generalized Collatz sequence is then defined as follows. C sub k from the positive natural numbers to the natural numbers. C0 belongs to the positive natural numbers. C sub n plus 1 is equal to f sub k of C sub n if C sub n is not congruent to 0 modulo 2k. G sub k of C sub n if C sub n is congruent to 0 modulo 2k. 3. Properties of the generalized Collatz sequences. 3.1 Trajectory in the generalized Collatz sequences. A trajectory of a strictly positive natural number C0 refers to the ordered sequence of terms obtained by successively applying the recurrence rule of the generalized Collatz sequence until the value 1 is reached for the first time, if it ever is. Thus, the trajectory includes the initial term C0, all intermediate terms, and stops as soon as 1 is reached for the first time. 2. The trivial cycle. For all k belonging to the positive natural numbers except 2 and 4. We have the following. For all k in the positive natural numbers, and for all n in the positive natural numbers, if n modulo 2k is not equal to 0, then the term following n is obtained by an iteration via the auxiliary function f sub k. and it is equal to the following. Since n belongs to the interval from 1 to 2k minus 1, n modulo 2k is equal to n. So S sub k of n is equal to 2k minus n. Then f sub k of n is equal to 1 plus 2k times n plus s sub k of n, which simplifies to n plus n times 2k plus 2k minus n. That is equal to n plus 1 times 2k. We also have the following. For all k in the positive natural numbers and for all n in the positive natural numbers. If n plus 1 modulo 2k is equal to 0, then the term following n plus 1 times 2k is obtained via the second auxiliary function, and it is equal to n plus 1. So from these two rules, and taking 1 as the first term of the generalized Collatz sequence, we obtain the following sequence. 1, 2 times 2k, 2, 3 times 2k, 3, and so on, up to 2k times 2k, and finally 2k. And since the term that succeeds 2k is equal to 2k divided by 2k, which is 1, we conclude that there exists a trivial generalized cycle of the form 1, 2 times 2k, 2, 3 times 2k, 3, and so on, up to 2k times 2k and 2k. Since 1 belongs to this cycle, the set consisting of 1, 2 times 2k, 2, 3 times 2k, 3, and so on, up to 2k times 2k and 2k converges to 1. Moreover, any a belonging to the interval from 1 to 2k minus 1 comes from g sub k of a times 2k. And we know that a times 2k with a belonging to the interval from 1 to 2k is an element of the trivial cycle. So all elements a in the interval from 1 to 2k minus 1 cannot be reached directly from outside the trivial cycle. For a equal to 2k, we know that it comes from g sub k of 2k squared. Thus, all elements a in the interval from 1 to 2k of the trivial cycle cannot be reached directly from outside the trivial cycle. For the elements of the trivial cycle of the form a times 2k, with a in the interval from 2 to 2k, we know that they come from f sub k of a minus 1, which itself is an element of the trivial cycle. But they can also come from g sub k of a times 2k, which is not an element of the trivial cycle. So the trivial cycle has 2k minus 1 gateways of the form a times 2k, with a belonging to the interval from 2 to 2k. These gateways are the only elements of the trivial cycle that can be reached directly from outside the cycle. 3.3 property. It can be shown that every non-zero natural number converges to a gateway of the trivial cycle of the form 2k times 2k before reaching 1. To demonstrate this, we define the inverse generalized Collatz sequence, denoted C inverse sub k. 3.4.1 inverse functions. First, G inverse sub k from the natural numbers to the natural numbers. G inverse sub k of n is equal to n times 2k. Next, let k be a positive natural number except 2 and 4, and let it be the exponent parameter. Recall that f sub k of m is equal to 1 plus 2k times m plus s sub k of m, where s sub k of m is equal to 2k minus m modulo 2k. This value is the smallest non-negative additive inverse of m modulo 2k, and it satisfies 0 less than s sub k of m less than 2k. We now define the inverse function f inverse sub k as follows. F inverse sub k of n is equal to n minus t divided by 1 plus 2k, where t is equal to s sub k of f inverse sub k of n, and t is the smallest strictly positive integer such that 1 plus 2k times f inverse sub k of n plus t is congruent to 0 modulo 2k. Domain of the inverse. The inverse function f inverse sub k is defined for all positive natural numbers n, such that n is congruent to 0 modulo 2k, and there exists a strictly positive integer t less than 2k, such that n minus t is congruent to 0 modulo 1 plus 2k. 3.4.2 Inverse generalized Collatz sequence. Let C inverse 0 belong to the natural numbers. C inverse sub n plus 1 is equal to the following. If C inverse sub n is congruent to 0 modulo 2k, then C inverse sub n plus 1 is equal to either f inverse sub k of C inverse sub n or g inverse sub k of C inverse sub n. If C inverse sub n is not congruent to 0 modulo 2k, then C inverse sub n plus 1 is equal to g inverse sub k of C inverse sub n. Assume that there exists a positive integer j such that c sub j is equal to 1. Then c sub j minus 1 is equal to g inverse sub k of c sub j. That is equal to g inverse sub k of 1, which is 2k times 1 equal to 2k. We have c sub j minus 1 equal to 2k. This value is not a gateway of the trivial cycle. Therefore, it can only be an element of the trivial cycle. Next, c sub j minus 2 is equal to g inverse sub k of c sub j minus 1. That is equal to g inverse sub k of 2k, which is 2k times 2k. We conclude the following statement. For all C0 belonging to the positive natural numbers, excluding 1 times 2k2, 3 times 2k3, and so on, up to 2k times 2k and 2k, if there exists a positive integer j such that c sub j is equal to 1, then there exists an integer m less than j such that c sub m is equal to 2k times 2k. 3.4.3 Theorem. Every natural number C0 excluding 1, 2 times 2, 3 times 2k, 3, and so on, up to 2k times 2k and 2k. If it converges to 1, then it first converges to 2k times 2k. Formal statement. For all k in the positive natural numbers except 2 and 4. For all C0 in the positive natural numbers excluding 1, 2 times 2k, 2, 3 times 2k, 3, and so on, up to 2k times 2k and 2k. If there exists a positive integer j such that c sub j is equal to 1, then there exists a positive integer m such that c sub m is equal to 2k times 2k, with m equal to j minus 2. 3.5 Property. For all k in the positive natural numbers, for all C0 in the positive natural numbers, and for all integers j, if c sub j is not congruent to 0 modulo 2k, then c sub j plus 1 is congruent to 0 modulo 2k and is equal to f sub k of c sub j. That is to say, every term not congruent to 0 modulo 2k is followed by a term that is congruent to 0 modulo 2k. For all k in the positive natural numbers, for all c inverse 0 in the positive natural numbers, and for all integers j, if c inverse sub j is not congruent to 0 modulo 2k, then c inverse sub j plus 1 is congruent to 0 modulo 2k and is equal to g sub k of c inverse sub j. That is to say, every term not congruent to 0 modulo 2k in the inverse generalized Collatz sequence is followed by a term that is congruent to 0 modulo 2k. For all k in the positive natural numbers, for all c inverse 0 in the positive natural numbers, and for all integers j, if c inverse sub j is congruent to 0 modulo 2k, then c inverse sub j plus 1 is equal to g inverse sub k of c inverse sub j, or equal to f inverse sub k of c inverse sub j, if c inverse sub j is a branch generator. That is to say, every term congruent to 0 modulo 2k in the inverse generalized Collatz sequence is followed by a term congruent to 0 modulo 2k, but it may also be followed by a term not congruent to 0 modulo 2k if the term is a branch generator. For all k in the positive natural numbers, for all C0 in the positive natural numbers, and for all integers j, if c sub j is congruent to 0 modulo 2k, then c sub j plus 1 is equal to g sub k of c sub j and is congruent to 0 modulo 2k, or it is not congruent to 0 modulo 2k if c sub j is not congruent to 0 modulo 2k squared. That is to say, every term congruent to 0 modulo 2k in the generalized Collatz sequence is followed by either a term congruent to 0 modulo 2k or a term not congruent to 0 modulo 2k. 4. Construction of the generalized Collatz tree. 4.1 Division of the positive natural numbers into subsets. According to the fundamental theorem of arithmetic, every strictly positive natural number can be written as a product of prime numbers in a unique way. For a given exponent parameter k belonging to the positive natural numbers except 2 and 4 of the generalized Collatz sequence, we define a partition of the positive natural numbers into subsets based on their prime factorization. Subset A sub k. If the factorization of a natural number n gives prime factors that are all equal to 2, and if the number of these prime factors equal to 2 is a multiple of k, then n belongs to the subset of natural numbers that are powers of 2k. This subset is denoted A sub k. A sub k is the set of all n such that there exists a natural number j with n equal to 2k raised to the power j. That is to say, A sub k is the set of natural numbers that are pure powers of 2k. The number 1 is included in A sub k since 1 is equal to 2k raised to the power 0. Subset B sub k. If the factorization of a natural number n gives prime factors such that the number of prime factors equal to 2 is strictly less than k, then n belongs to the subset B sub k. B sub k is the set of all n that are not divisible by 2k. That is to say, n modulo 2k is not equal to 0. We have the following intersections. A sub k intersect B sub k is equal to the set containing 1 if k is equal to 1. Otherwise, A sub k intersect B sub k is the empty set. This is because for k equal to 1, the number 1 is represented as the beginning of the trunk, but also as the smallest, namely a branch beginning with rank 1. Subset M sub k. If the factorization of n gives prime factors that are not all equal to 2, and the number of prime factors equal to 2 is greater than or equal to k, or if the factorization of n gives prime factors all equal to 2, but the number of such factors is greater than or equal to k and not a multiple of k, then n belongs to the subset M sub k. M sub k is the set of all n such that n is equal to p times 2k raised to the power j, where p is not congruent to 0 modulo 2k and j is greater than or equal to 1. We have M sub k intersect A sub k is the empty set. Thus, we obtain the partition. The set of positive natural numbers is equal to the union of A sub k, B sub k, and M sub k. 4.2 Description of the generalized Collatz K-tree. We define the K-tree as the tree structure generated by the generalized Collatz function. 1 plus 2k times n plus s sub k of n, and n divided by 2k. Here, k belongs to the positive natural numbers except 2 and 4, and is the exponent parameter. The Collatz K-tree represents the set of strictly positive natural numbers that converge to 1 for the given value of k. The representation of these numbers is based on the rank of the integer. Definition of rank. The rank of a natural number n, denoted rank of n, is defined as the number of iterations of the inverse function f inverse sub k required to reach the value n, using the inverse Collatz sequence and starting from 1 as the initial term. To determine the rank of a natural number and its representation in the Collatz K-tree, it is not possible to deduce it directly from n using the inverse sequence. Instead, it is necessary to verify whether n converges to 1, determine the rank of n, and determine the number of successive applications of g sub k required to move from one term not congruent to 0 modulo 2k to the next such term. We agree that whenever we refer to the notions of K-tree, rank, or generalized Collatz sequence, we are considering a fixed exponent parameter k belonging to the positive natural numbers except 2 and 4. According to the generalized Collatz sequence, for each term there is only one possible next term. This implies that every natural number has a unique trajectory. Therefore, every natural number that converges to 1 has exactly one unique representation in the Collatz K-tree. 4.2.1 Properties of the elements in subset A sub k. Consider k belonging to the positive natural numbers except 2 and 4. For all initial values c0 belonging to A sub k, with c0 strictly greater than 1, we have c0 equal to 2k raised to the power j for some positive integer j. Then the next term c1 is obtained by applying g sub k. c1 is equal to c0 divided by 2k, which is equal to 2k raised to the power j minus 1. By repeating this process, after j iterations, we obtain 1. Therefore, for any c0 belonging to A sub k and greater than 1, c0 converges to 1. For c0 equal to 1, we have previously shown that 1 converges to 1, since it is an element of the generalized trivial cycle. Thus, for all c0 belonging to A sub k, C0 converges to 1. The elements of the subset A sub k are represented by a vertical line. This vertical line is called the trunk of the Collatz K-tree. The elements of the subset A sub k have rank 0. Elements of M sub k. Let n belong to M sub k. By definition, n is equal to p times 2k raised to the power j, where p is not congruent to 0 modulo 2k and j is greater than or equal to 1. Applying g sub kj times to n, we obtain p. Since p belongs to b sub k, every element of M sub k is transformed into an element of b sub k after a finite number of g sub k iterations. Therefore, if all elements of b sub k converge to 1, then all elements of M sub k also converge to 1. This can be expressed as follows. For all n in b sub k, if there exists a positive integer j such that c sub j equals 1, then for all m in M sub k, there exists a positive integer I such that c sub I equals 1. Conclusion. We have shown that for all k belonging to the positive natural numbers except 2 and 4, all elements of the subset A sub k converge to 1. If all elements of the subset B sub k converge to 1, then all elements of the subset M sub k also converge to 1. Since the union of A sub k, B sub k, and M sub k is the set of all positive natural numbers, we obtain the following theorem. 4.24 theorem. The convergence to 1 for all positive natural numbers is equivalent to the convergence to 1 for all elements of the subset B sub k, that is, for all numbers not congruent to 0 modulo 2k. 4.2.5 Representation of elements from B sub k and M sub k. Each element n belonging to B sub k that converges to 1 is represented by a distinct point on the Collatz K-tree. Each element m belonging to M sub k, which is reducible to an element n of B sub k, meaning that m is equal to n times 2k raised to the power j, with n greater than 1 and j greater than or equal to 1, is represented on a half-line starting from the point n. This half-line is called a branch. The origin point n is called the beginning of the branch. A branch can be a mother branch emerging directly from the trunk or from another branch, or a daughter branch emerging from a mother branch or from the trunk. 4.2.6 Exception. For the number 1, it is represented on the trunk and also represented as a branch beginning without representing the elements of M sub k, otherwise the trunk would be reproduced again. From the trivial cycle consisting of 1, 2 times 2k, 2, 3 times 2k, 3, and so on, up to 2k times 2k and 2k, we deduce that the rank of 1 is equal to 2k minus 1. 4.2.7 Branch Generator. A branch generator is a natural number that belongs either to the trunk or to a mother branch. That is to say, it is an element of A sub k or M sub k. A non-zero natural number g is a branch generator if and only if f inverse sub k of g is equal to n, where n is a branch beginning. That is equivalent to saying g is equal to 1 plus 2k times n plus s sub k of n. The connection between a branch and its mother branch, or the trunk, is represented by an inclined line segment running from the top, the branch generator, down to the bottom, the branch beginning. 4.2.9 Sister branches. Two branches are called sister branches if and only if they have the same mother branch, or if both are daughter branches of the trunk. Recognition of structural patterns in the dynamics of the generalized Collatz. 5.1 The form of a branch generator. Let G belong to M sub k. The number G is a branch generator if and only if there exists an element n in B sub k such that G is equal to F sub k of n. This is equivalent to saying that there exists n in B sub k such that n is equal to F inverse sub k of G. We observe the following. If there exists n in B sub k such that G is equal to F sub k of n, then G is congruent to 0 modulo 2k. The smallest possible branch generator must be greater than or equal to any gateway. Therefore, the smallest branch generator is equal to 2k times 2k. We also have the following. If there exists n and b sub k such that n is equal to f inverse sub k of g, then there exists a value s sub k of n between 1 and 2k minus 1 such that g minus s sub k of n divided by 1 plus 2k is equal to n. The quantity s sub k of n is always not congruent to 0 modulo 2k. 5.1 theorem. A natural number g is a branch generator if and only if all of the following conditions hold. First, g belongs to m sub k. Second, g is greater than or equal to 2k times 2k. Third, there exists an element n in b sub k such that g minus s sub k of n divided by 1 plus 2k is equal to n. 5.2 The first branch generator. We now ask the following question. How many times must we multiply a branch beginning or the beginning of the trunk by 2k in order to obtain the first branch generator? We begin by proving the following statement. If D1 and D2 are two branch beginnings that come respectively from branch generators G1 and G2, and if D1 is strictly less than D2, then G1 is strictly less than G2. To prove this, assume D1 is strictly less than D2. Then D1 multiplied by 1 plus 2k is strictly less than D2 multiplied by 1 plus 2k. Since the smallest possible value of D2 is D1 plus 1, we obtain D2 multiplied by 1 plus 2k is greater than or equal to D1 multiplied by 1 plus 2k plus 1 plus 2k. This implies D2 multiplied by 1 plus 2k is strictly greater than D1 multiplied by 1 plus 2k plus 2k. We also have the absolute difference between s sub k of D1 and s sub k of D2 is strictly less than 2k. Combining these inequalities, we obtain D2 multiplied by 1 plus 2k plus s sub k of D2 is strictly greater than D1 multiplied by 1 plus 2k plus s sub k of D1. Therefore, D1 strictly less than D2 implies G1 strictly less than G2. 5.2.1 Representation of a branch beginning. Let n be a branch beginning. This means that n belongs to b sub k, or n is equal to 1, the beginning of the trunk. Thus, n belongs to the union of b sub k in the set containing 1. For all such n, we have the following representation. N can be written as where j is a natural number. Therefore, for all n belonging to b sub k or equal to 1, if we multiply n by 2k raised to the power I, we obtain g equal to 1 plus 2k raised to the power j times 2k raised to the power I, plus phi times 2k raised to the power I. If g is a branch generator, then there exists an element d in b sub k such that d is equal to g minus s sub k of d divided by 1 plus 2k. From this, we obtain d is equal to j times 2k raised to the power I plus phi times 2k raised to the power I minus s sub k of d, all divided by 1 plus 2k. The smallest number of times we must multiply n by 2k in order to obtain a branch generator is the smallest positive integer I such that there exist values j, phi, and d, satisfying the following conditions. J is a natural number. Phi belongs to the interval from 0 to 2k. If j equals 0, then phi is strictly positive. D belongs to b sub k. S sub k of d belongs to the interval from 1 to 2k minus 1. 5.3. The smallest successor of a branch generator. Let D1 and D2 be two branch beginnings generated respectively from G1 and G2, such that G1 is strictly less than G2. We have G1 is equal to 1 plus 2k times D1 plus S sub k of D1. G2 is equal to 1 plus 2k times D2 plus S sub k of D2. We also have G2 is equal to G1 times 2k raised to the power I. We now ask, what is the smallest positive integer I such that D1 times 2k raised to the power I is not equal to D2, and S sub k of D1 times 2k raised to the power I is not equal to S sub k of D2. Let phi be a positive integer. We can write G2 as 1 plus 2k times the quantity D1 times 2k raised to the power I plus phi, plus the quantity S sub k of d1 times 2k raised to the power I minus 1 plus 2k times phi. Thus, we must find the smallest positive integer I such that there exists a phi satisfying the following conditions. First, S sub k of d1 times 2k raised to the power I minus phi times 1 plus 2k belongs to the interval from 1 to 2k minus 1. Second, d1 times 2k raised to the power I plus phi is not congruent to 0 modulo 2k. 6. Conclusion. The structural analysis of the generalized Collatz tree, also called the K-tree, has revealed that its organization does not replicate the exact structural formulas observed in the classical Collatz tree. While several analogies persist, particularly in the behavior of branch beginnings and their hierarchical propagation, the generalized framework exhibits distinctions that require deeper investigation before a complete structural correspondence can be established. In this preprint, our exploration of the K-tree was intentionally limited. A full structural characterization of the generalized tree, including closed-form descriptions of ranks, branch generators, and their asymptotic behavior, has not yet been undertaken.